Hello and welcome to CE3105 Mechanics of Fluids at Texas Tech University. In today's lab, we'll be looking at open channel flows, and more specifically, we'll be estimating unknown Manning's coefficient for our hydraulic flume. So what are open channels? Open channels are either natural or man-made conduits where water flows with a free surface. When we say the water flows with a free surface, there is at least one surface of the water that's open to atmosphere or is not constrained in any other way. So if we compare open channels to pipe flows, in pipe flows we have the water that's constrained by the walls of the pipe, which completely cover that water. But in open channels, at least one side of the open channel of the channel is open, so it's open to atmosphere. Okay, open channels occur frequently in nature. So we have rivers, streams, creeks. These are all natural open channels, and clearly, when we are interested in flow of water through them, particularly floods, we are interested in knowing how fast the water would move or how much water would move through these channels. In addition, civil engineers also build open channels to convey water. So we have canals, sewer lines, partially flowing culverts are some examples of open channels or structures that act as open channels. So in general, open channels are used to carry large volumes of water over long distances, and open channels are used when the quality of water is not of concern. In particular, as we move, and the quantity of water that needs to be moved is very significant. Open channels, by and large, use gravity to move water from one location to another. So in terms of energy costs, it's a lot cheaper to move large volumes of water using open channels because the gravity helps move that water from one location to another. So what factors affect flow through open channels? As I said, the flow in open channels is mostly under the influence of gravity. So the slope of the channel plays a big role. Clearly, the steeper the slope, the faster the water would flow. However, this water is in contact with the bottom and the sides of the channel. So there is frictional resistance to the flow rate that's offered by the bottom and the sides where the water comes into contact with the channel. So friction resistance also depends upon the geomorphology of the stream, whether we have very large rocks or fine particles at the bottom of the stream or in our channel. In addition, vegetation can also play and also often plays a very important role in controlling the flow of the open channel. So to put it very simply, the flow in an open channel is a net effect of gravitational and frictional forces, and frictional forces come where the water is in contact with the channel, and in addition, the geomorphology, the presence of rocks and vegetation, and the meandering of the channel, all of them can play a role in defining that flow. So open channel flows can either be uniform or non-uniform. When we have uniform flow, what it means is that the depth and the velocity profile is same at all sections. So here I show two sections of the open channel. Clearly there is a slope, so the water is moving along that slope. But if you look at the velocity profiles, that velocity profiles stay constant between points 1 and 2, which are at two different locations on that channel. So when that happens, then we have uniform flows. Uniform flows are very rarely seen or seldom seen in natural systems, but it's easy to see uniform flows in laboratory settings. And uniform flows provide a good baseline for us to compare other types of flows in open channels. So they are of interest to us. Steady state flow in an open channel implies there is no change in depth or velocity over time. So the height of the water stays the same and the volume of the water or the velocity of the water is same at all instances of time. Again, steady state is an idealized condition in open channels, natural open channels in particular, but again provides us a good reference to look at other conditions of flow. Right. So understanding uniform flows and non-uniform flows in open channels are important. And again, if you look at the velocity profile, we have the bottom friction, which causes the no-slip boundary condition. So the flow or the velocity at the bottom is equal to zero, and then that velocity keeps increasing and is the maximum at the atmosphere-water interface, just because there is no resistance being offered to the flow at that point, because the air offers very little resistance compared to other flow lines of water inside that channel. So there are several equations that have been used or have been put forth to define flows in open channels. Most of these equations have been defined empirically, although they're based on momentum balances under idealized conditions. So one of the very famous equations that we use in the US very commonly is what's known as the Manning's equation. And what Manning's equation tells us is that the flow velocity is a function of the slope, which is used to account for gravitational effects, as well as hydraulic radius, which accounts for channel geometry effects. So if we look on the right-hand side, the velocity v is equal to c sub naught, which is a constant, which is equal to 1 in SI units and 1.486 in English or US customary units. The hydraulic radius is raised to power 2.3, and then square root of s being the channel slope. So this hydraulic radius r is defined as the cross-sectional area over the wetted perimeter. The wetted perimeter is the channel that is in contact, the length of the channel that's in contact with water. So we calculate velocity using Manning's equation, and then of course we can use Manning's equation in conjunction with continuity equation to get our flow rate. So the flow rate Q is equal to A times V, which is area times the velocity of the cross-sectional area times the velocity, and we get that is equal to cross-sectional area times C naught over N, R raised to the power 2/3 square root of S. So this gives us a way to estimate flow rate in open channels. So to take a deeper look at that hydraulic radius, so let's look at an idealized rectangular channel. So I'm looking at a cross-section of a channel. The cross-sectional area will be equal to the width of the channel times the height of the water. So that's equal to W times H. And the wetted perimeter is equal to this H, where the water is in contact with the open channel, this W, which is the bottom, where the water is in contact with the open channel, and then H, this H, which is the height of the side of that open channel where the water is in contact with that channel. So if I add W plus 2 times H, I get my perimeter. So the wetted radius, so hydraulic radius is area over the wetted perimeter, which is equal to W times H over W plus 2H. So clearly, the wetted perimeter is the perimeter of the channel is in contact with water, and of course, the cross-sectional area is defined as below. And as you can see, the cross-sectional area depends on the height of the water, and of course, the height of the water depends on the flow rate of the water. So we have highly nonlinear relationships between the height and the discharge and the velocity, which is manifested in that Manning's equation. The hydraulic radius and the wetted perimeter clearly depend upon the channel geometry. Here I'm only showing it for a rectangular channel. Of course, if you have a trapezoidal channel or some irregular channel, that geometry is going to vary. It's a little bit easier to calculate wetted perimeters in engineered channels where we have constructed channels as opposed to natural channels, which tend to have much higher irregular geometry. But nonetheless, the basic idea is to estimate to get the cross-sectional area and the wetted perimeter of the channel, and use that in conjunction with Manning's equation to calculate our velocity and flow rates. So the Manning's N is another parameter. The Manning's N is a measure of the frictional resistance that's applied to the flow by the channel. And Manning's N depends on a variety of conditions, particularly the channel material, as well as the conditions in the channel. Conditions in the channel such as the irregularity in the channels, meandering of the channels, presence of vegetation or other obstructions like big rocks. All of these affect the Manning's coefficient. Typically, during engineering design, we go to tables such as the ones I show here and pick a typical value of Manning's coefficient. and use that in our design calculations. But what we're going to do in today's lab is actually measure this Manning's coefficient in an open channel. One other thing that we want to do in today's lab is to look at hydraulic jumps. And hydraulic jumps happen when fast-moving water comes into contact with a slow-moving water, or water that's stagnant. So the fast-moving water, the flow is called supercritical flow when you have Froude number greater than 1. And that's coming in contact with flow that's very slow, or subcritical flow, where the Froude number is less than 1. And as this high water with high kinetic energy comes into contact with this low kinetic energy water, what happens is some of the kinetic energy is converted into potential energy. And that conversion causes the water to rise, and that's what we call as a hydraulic jump. As this process happens, there is considerable amount of energy that's lost due to turbulence, so which causes the water to slow down. Hydraulic jumps can occur both naturally or can be engineered. We typically engineer hydraulic jumps at the bottom of a spillway or a control gate of a dam to reduce the velocity of the incoming flow, the flow that is coming out of the dam, to make sure that we don't have flooding or scouting that is happening at downstream. There are some downstream effects, but hydraulic jumps can also cause scouting, which can cause structural damage and sediment movement. So controlling this hydraulic jump is important to make sure that for the integrity of the structures, but it's also important to have some hydraulic jumps, particularly in dams sometimes, to reduce the velocity of the flow of the incoming water. Um, Hydraulic jumps, of course, can be stationary, they can be moving, and they can also occur under submerged conditions. So there are a variety of times when hydraulic jumps happen, and of course, sometimes, as engineers, we would like to control these hydraulic jumps to make sure that they don't cause damage and they work to our advantage in terms of reducing our flow velocities. So what we are going to do today is we're going to go to the lab and look at this flume. The flume has got two pumps inside, and we have these knobs which control our flow rates. So as we change the flow rate, the manometer here gives us a pressure difference associated with that flow rate. There is an orifice plate there, and the manometer basically is reading the flow before and after that orifice plate. And that deflection can be used in conjunction with this calibration curve to obtain our flows. Okay, so once we get our flows, so we look at the deflection in the manometers, which is the difference between the two manometers, and then read off the large orifice. Your handout also has an equation for it that you can use to plug in and get your flows. And then once you get the flow, you measure the width of the channel and the height of the channel. And once you record that, you can calculate your cross-sectional area, your wetted perimeter, and calculate your hydraulic radius. You can also control the slope of your channel by moving the flow in and out. So that slope gives you different. So you do this experiment for different slopes, and then once you do the experiment for different slopes, you can plug in your slope, your hydraulic radius, and using your flow rate, estimate your Manning's equation. And also you can take your flow rate and every other term except that 1 over n and plot a graph, and the slope of that graph will be equal to the reciprocal of the Manning's coefficient, from which you can estimate your Manning's coefficient as well. And once you get your Manning's coefficient, you're going to compare it with tables to see how well your Manning's coefficient compares to that given in the literature. So that's the basic idea behind today's experiment. And we'll also, this hydraulic jump, this flume also has a sluice gate or a gate at the very bottom. And by opening the gate up, or moving the gate up, we can actually create subcritical flow conditions in this end of the channel, and then we have the water flowing over an orifice, so that gives us supercritical flows. And then when the supercritical flows meet the subcritical flows, we are going to create a hydraulic jump. So we're going to have a demonstration of hydraulic jump in this class as well. So at the end of this lab, you should know what are open channels, what are they, how are they different from pipes, and why do civil engineers study open channel flows, Manning's equation, how to use Manning's equation to get the velocity in an open channel, and then the Manning's equation plus continuity for estimating flow rate, and then using Manning's equation to estimate unknown Manning's coefficient, so using the Manning's equation to estimate the unknown Manning's coefficient. So those are the objectives, and then of course have an understanding of what hydraulic jump is as well. So those are the basic objectives of today's lab. Thank you.